we are ready.
Assalamu alaikum wa rahmatullah, and welcome to all of our respected viewers to the Voice of the Cape's YouTube channel as well as the Voice of the Cape's Facebook page. Alhamdulillah, it gives me great honor and pleasure to once again introduce Brother Imad Isaacs of Futures Academy, South Africa's online high school. And today, inshallah, will be the first session for this week, particularly the first session of the physical sciences paper, this course that will be given over by Brother Imad Isaacs on behalf of the Futures Academy Online High School. And this is, of course, the Voice of the Cape's Matric revision program that we are running for this year for 2023, and of course, dedicated to all of the matriculants out there who are preparing for the trial examinations, the mock examinations, as we say locally, as well as for the NSC exams, inshallah ta'ala. This is indeed a collaboration between the Voice of the Cape as well as Futures Academy SA Online High School. And for today, we hand over to Brother Imad Isaacs, who will be conducting the Physical Sciences Session 1 session, inshallah ta'ala. Brother Imad, all yours, inshallah. Bismillah.
Okay, shukran, Brother Amir. Shukran so much. So inshallah, as our brother has mentioned, that we will be focusing on physical sciences. So welcome to the program, the first of hopefully 10, maybe 8 to 12 sessions, inshallah, there around. Okay, so as mentioned, it is physical sciences final exam preparation sessions. There's a number of topics that actually align between grade 11 and grade 12 that is tested in the National Senior Certificate Examination. So over the next few weeks, you are more than welcome to invite all your grade 12 peers that take physical sciences, as well as, where relevant, grade 11 learners as well. So inshallah, let us get started. Okay, before we delve into the technical matters and actually into the program and the meat thereof, let us look at the examination performance over the last few years. Okay, so unfortunately, we did not get a chance to paste in the 2022 statistics. But if we look at the overall achievement rates in physical sciences between the years 2017 to 2021, and the last 5 years particularly, we will notice that, of course, to pass the subject, you can pass with a 30% or a 40%. And we see that the bulk of the country, 69% of learners, achieve a pass in physical sciences in 2021, and that is 69%. However, only 44.8% of that, just over a quarter of those that pass, actually fall between 30 and 40, right? And then we have learners who are achieving at 40% and higher, and that's just shy of about half of the learners that take the subject, that is 44.8%. Okay. Generally, you see slightly higher maths pass rates, but the overall absolute number of learners in Matric that actually pass physics will, of course, be less, because there are less students who take physical sciences compared to mathematics. Okay. Then if we look at the next chart over here and we compare the performance in terms of the distributions, we know that there are 7 codes. And in terms of the 7 codes, they range from 0% all the way up to 80%, and 80 to 100% being the final category. Now, those achieving an A, which is a distinction, makes up a very tiny percentage of the proportion of learners. Generally, we can see there it's probably around 3%. In 2017, 3.1% of the learners actually got a distinction. And those, about 1.3% in 2017 achieved an A plus, right? Or a grade of 90 to 100. Okay. And just shy of 1% of learners actually have been achieving between 90 to 100%, with 2.4% of those that write the subject and pass the subject achieving a distinction. Okay. Now, having said that, we do want to mention to you specifically that it's not that hectic to get a good mark in physical sciences. The concepts are fairly easy to understand, but it does definitely take quite a bit of practice as well. Okay. If we look at the structure of the exam question paper, you are very familiar that at this stage you know that there are 2 examination papers. One is focused on the physics, and the other question paper is focused on the chemistry. So paper 1 is physics focused and paper 2 is chemistry focused. In terms of the subcategories for paper 1, we have mechanics, wave, sound and light, electricity and magnetism, and then matter and materials, okay? So there's 5 broad topics that are tested in the physics paper. And then there's 2 major areas for the chemistry focus. That's chemical change and matter and materials. And then you can also see that we've broken them up into various categories over there. Matter and materials, 58 marks. Chemical change, approximately 92 marks. And then mechanics and electricity, that makes up the bulk of your paper in paper 1. Okay, so a lot of the work is focused on mechanics and electricity and magnetism in terms of the paper 1 content. Now, just as we spoke about mathematics being divided into various cognitive levels, going from level 1 all the way through to level 4, with physical sciences, we also find similar cognitive levels. Okay, this would usually involve some analysis, this would involve some degree of synthesis, and then obviously level 1 questions are those questions that are direct recall. Okay, where anyway we're looking at about 15, sometimes even 17% of the examination paper. Okay, right, and you also know it's 150 marks, with each paper being 3 hours in duration. Okay. Now, just continuing in terms of the structure of the examination, there's also content that is selected from grades 10 and grade 11 that you must be familiar with. A significant portion of the examination that is tested in the mechanics section deals with physics coming from grade 11, and that is your Newton's laws, Newton 1, Newton 2, and Newton 3, as well as Newton's laws of universal gravitation, or Newton's law of universal gravitation, my apologies, and the application of Newton's laws in various contexts. You've also been exposed to electric circuits coming from your grade 10 content, and you've gone through it in a bit more detail and applying Ohm's laws and studying ohmic conductors and so forth in grade 11. That is also tested in the Matric final examination. And then finally, electrostatics content that you've learned in grade 10 is also relevant for the Matric final examination. That is the content that you must know from the physics component that comes from your previous grades. Then with respect to chemistry, there's certain content that has been covered in grade 10 and grade 11, and that is representing chemical change, knowing your intermolecular forces, being able to identify them, knowing the strength of their bonds, and also knowing your intramolecular forces as well. Stoichiometry or stoichiometric calculations, that is also relevant from grade 11, as well as the chapter on energy and change. Okay, now in terms of physics paper 1, today we're going to be focusing on one of the key skills required for answering questions in both paper 1 and paper 2. Today's focus, which I'll get to in a moment, but before we do that, let's talk about this exam paper structure. Okay. Of course, question 1 is generally a multiple choice question consisting of 10 questions across various topics. Okay. And just because it's multiple choice questions doesn't mean you're just supposed to randomly select an answer. Okay. In one of our sessions during the revision program, we'll specifically focus on MCQ strategies and how to answer them. Then questions 2, 3, 4, and 5 for the DBE examinations in physical sciences paper 1 generally focus on mechanics. The question 2 is always a Newton's second law question. Question 3 is vertical projectile motion. Question 4 is momentum, and question 5 is a work, energy, and power question. And all of them together make up the section on mechanics. For question 6, we have the Doppler effect, which is the section on wave, sound, and light. And then question 7, 8, and 9 focuses on electricity, testing electrostatics, circuits, and motors and generators. And then the last section, which deals with matter and materials, focuses on the photoelectric effect, and that is question 10. And then in terms of the marks, here you can see the average marks per question. They might differ by 1 or 2 marks per question, and there you can see that they are fairly consistent year in and year out. Okay. And those are the marks of 2019, 2020, and 2021. Right, so of course, question 1 itself is the MCQ, and that's always weighted at 20 marks. Okay, so Unfortunately, the banner on screen, we can't really see the just slightly below here, but I'll tell you what it says. Below 57, it says mechanics. Below the number 11, it says waves. And below 49, it says electricity. And below 13, it says M&M, which is matter and materials. And so now you can see that the bulk of your marks actually lie in mechanics and electricity. So they are fairly big sections, right? Which means if you actually focus on the mechanics and the electricity, you can do quite well in the examination if you focus on those two components. Now, having said that, the sections on Doppler effect, which is question number 6, and also question number 10, which is the photoelectric effect, those are very, very easy, fairly straightforward, simple questions. They can become a little bit complex if the examiner wants to make it tricky, but I would consider the Doppler and the photoelectric effect to be those sections that would be confidence-boosting ones. So in other words, if you are starting out to study, go over those sections, get it out of the way, but don't spend too much time on that. Okay. Over the next few weeks, we will focus on graphs, equations, ratios, and MCQs. We'll also touch on free body diagrams. And then we'll also speak specifically today about what are recall applications. Okay. In addition to that, we will also spend specific lessons in the revision program focused on areas where learners have significantly underperformed according to the NSC diagnostic reports. An example of that would be KC calculations. Okay, we find that sometimes less than 40% of the country actually do well in the KC calculations. So that's one example. Okay, right. This may potentially be anecdotal reasons for underperformance. Now, generally, we are of the opinion that students generally underperform in the physical sciences examination due to one of two reasons, and sometimes both. The first being a poor conceptual understanding. Now, generally when speaking about physics, the physics in terms of the real world is not too hectic to understand, but the language of physics is mathematics. So often, sometimes a student may understand the concept, but they suffer because of poor mathematical skills. In other words, they cannot manipulate an equation, or they cannot read or interpret graphs or construct graphs. So that's what we mean they have poor mathematical skills. And for that reason, the poor mathematical skills, graphs, equations, and ratios are actually highlighted over here. Fortunately, with physical sciences, it is not hectic math skills that you need. You need some equations, you need some graphs, you need to understand the basics of manipulating ratios, and it should be more or less okay. Okay. And sometimes you get students who have good maths marks, meaning they can manipulate things, they can do some of the basics, and they're fairly confident in mathematics as a subject, but they actually lack the understanding of what's happening in the physics, and sometimes there's a combination of both. Okay. Right. In terms of skills for physical sciences, if we refer to the CAPS document, we can find a list of skills, and they tell you things like models, scientific notation, changing the subject of the formula is a skill. Basic trigonometric skills, right? Defining the various ratios, sine, cos, and tan. Understanding what is a rate is also a basic skill. And then obviously ratio and proportion, that's when we look at direct and inverse proportions and so forth. Okay. Okay. Now, let's talk about what are recall applications. In terms of recall applications, in the examination guidelines, there are 3 important documents every student should ideally have at their disposal, and that is, number 1, the examination guidelines. Now, in the year 2023, the latest examination guidelines is the 2021 examination guidelines. So that means this is an up-to-date set of guidelines. Don't use any other than that. If you are unsure of where to find this, you can always go to education.gov.za. Whoa. Let's try www in case they don't have an Apex domain there. Yes. You go to curriculum, you should be able to go to the National Senior Certificate Examinations. And somewhere, usually on the side over here, you will find the examination guidelines. Okay. So on the DBE's website, curriculum, National Senior Certificate, and then you go down and you find 2021 examination guidelines. Okay, so I'll give you a moment to just quickly look at that. Okay, so once you've had a look at that, you can find all the examination guidelines for all your subjects listed on the DBE's website, and you should find it over here. Anyway, coming through, let's go back to this document quickly. Okay, so in the examination guidelines, you will find all the content that will be examinable for the NEC exam. Okay.
Assalamu alaikum wa rahmatullah, respected viewers. Just as a reminder, inshallah, we are continuing with session 1 very soon, and that is pertaining to the physical sciences paper. And of course, the instructor is none other than Imad Isaacs from the Futures Academy SA Online High School. And of course, as Brother Imad indicated, to all of the matriculant students out there, everyone who's preparing for their trial examinations, their mock examinations, please make use of the DBE website where you may find all the past papers to equip you with the necessary information as well as guidelines in order that you may succeed with your exam preparation. But for now, we hand back to Brother Imad to continue with the presentation on session 1, physical science paper, inshallah.
Okay, apologies for that. Shukran so much, Amir. Okay, just continuing. Right, so the examination guidelines, there are still students who study for the NSC examinations and they don't make use of the exam guidelines. The examination guidelines is basically a detailed scope for what will be tested in the final NSC exam for paper 1 and paper 2. So make sure that you spend time going through this, right? Spending time going through this to actually see what will be tested, right? It's detailed there and it's very, very good, particularly for the subject physical sciences. In other words, it's an excellent set. Now, some of the other subjects don't have as detailed or as nice examination guidelines. Okay. Righto. So coming back to what we mentioned over here is the recall applications. So what are recall applications and what do we refer to them as? So in the exam guidelines, there are certain things that you must know, and those are definitions, right? So for example, when you're learning definitions for physical sciences, you learn them straight from the examination guidelines. For example, define normal force. Well, it's the force or the component of a force which a surface exerts on an object with which it is in contact and which is perpendicular to the surface. Define frictional force as the force that opposes the motion of an object and which acts parallel to the surface. Okay. Example and so forth. Static frictional force, kinetic frictional force. So all of these are exam guidelines. Okay. Definitions that you must be familiar with. So you study them directly from the examination guidelines. Okay. State Newton's first law of motion. Then they tell you what Newton's first law of motion is. Right. Newton's second law of motion. Again, there's your definition. So spend time with the examination guidelines going through this, and you will find that the definitions for chemistry are also there. Momentum, the product of an object's mass and velocity. Describe linear momentum, right? Newton's second law in terms of momentum. So familiarize yourself with that. So we're not going to really spend time on that. We just want to show you where it is, how you can find it. And then we want to go to an example of a question paper that gives you these marks. So if we start over here, okay, this is an example of direct recall questions. Some of those are fairly easy, but let's go to the actual section B, which contains the questions. Right, so if we start here, state Newton's second law of motion in words. Right, so there we go. Start counting with me. Here we have 2 marks already. Okay. 2 marks. So that's an easy definition question over there. Then if we go define the term free fall, that's another definition. And if you go to the exam guidelines, you will find that you have free fall there defined as the motion during which the only force acting on an object is the gravitational force. So clearly free fall is there and it's fairly easy. And there you can see it's another 2 marks. At this point, we're really sitting at 4 marks. Okay, and that's more than 2% of the paper already. Okay, there we go. Let's continue further. State the principle of conservation of linear momentum. Okay, that means momentum before is momentum after. You can look at a longer definition as well. Right, you will find it in here. Okay, conservation of momentum. Yeah, conservation of momentum to collision, distinguish between elastic and elastic. I'm just trying to see. Yeah, state the principle of conservation of linear momentum. So here we go. The total linear momentum of an isolated system remains constant. So now you're sitting already at 6 marks. Okay, so that's actually 2% is 3 marks. So we're sitting at 6 marks. So that's 4% of an examination paper you already have in the bag for just memorizing a few basic definitions. Okay, if we continue further, we have another term here, non-conservative force. Okay, so if you go there, conservative force. Okay, define a conservative force, define a non-conservative force, and there we go. Another example. Right, and there's a few examples thereof. So you take these definitions directly from the examination guidelines. Okay, then if we go to this question over here, we're at question number 6. It says, name the phenomenon illustrated by the graph. Okay, that's also an example of a direct recall question. And relationship between the observed frequency and the frequency of sound waves emitted by a stationary source. So you are very familiar that this is the Doppler effect, because instead of telling you to define it, they're now giving you what it is, and they're asking you to identify it. So again, fairly simple. Right, so state Coulomb's law in words. I think we were at 6 marks, now we're at 7, now we're at 8, 9 marks. Okay, so at 9 marks, I think we are sitting at 6%. Right, if we continue further, state Ohm's law in words. Okay, you're at 11 marks now. Okay, and then another one here, 11 plus 2 is 13 marks. Define the term EMF. Right, that's again in the examination guidelines. If we go a little bit further, name the component of this generator to ensure that the induced current external circuit is in one direction only. That will be a split ring commutator. That's also an example of a direct recall question. So, I mean, you could potentially add it to your 13, make it 14 marks at this stage. Righto. And define the term work function, another definition there. So we're sitting at about 16 marks right now. So you and I both know that 16 marks is quite a bit. It's just over 10% of the examination paper. It's just over 10% of the examination paper. Okay. Okay. So if we go to a paper in November 2021, we can see the consistency very quickly. Which one? Here they give you a definition: the perpendicular force exerted by a surface on an object in contact with the surface. So if we have to highlight this, we're sitting again here with 2 marks. In the ball side, which one of the following physical quantities will be the same for both balls? Okay, maybe a little bit of direct recall there. Okay. Right. So we're sitting with 2 marks plus another 2 marks is 4 marks. Okay. Let's see as we scroll. 4 plus another 2. Give the definition or explain the meaning of. That's going to be 6 marks. Principles of conservation of mechanical energy, describe it or state it in words. So we're now sitting at 8 marks. Okay. 8 plus 2, we're sitting at another 2, it's 10 marks. Define the term power, 12. Name the component, again another recall, easy application question. So 12 plus 1 is 13 marks. Define the RMS potential difference, 13, 14, 15 marks. So we're 15 marks now. Okay. And then if we go to the end, 15 plus 2, we're sitting with 17 marks that we can consider giveaway marks just coming straight from the definitions. Okay. So on this point, we haven't gone into all those definitions. The point is for you to go through the examination guidelines. You can even Google a summary sheet that has been made from the examination guidelines and make sure you learn all of the definitions, okay? Because again, if you're sitting with 17 marks coming from the exam guidelines, that is just definitions that anybody could learn in a day, the day before the exam as well, then you know that you're capable of doing that, right? So you're sitting with 11 or 12% in the bag already. Okay, so here we've just noted exam guidelines is what you need to use to study the definitions, and you've seen quite a bit of examples, anywhere over 10% of the paper, 10, 12% of your examination paper actually coming from just giving them those definitions. Okay, now we move to the next skill. We need to talk a little bit about graphs. We have about 25 minutes remaining. In terms of graphs, right, what is a graph? Well, graphical representation of certain relationships, right? So here's 3 examples of graphs. Number 1, you can see a rate graph. And what is a rate graph? We can't actually see the bottom of this graph over here, but it's got the time in seconds. This graph over here has got volume. And then, of course, this is an example of something being measured with respect to time. So there are examples, a velocity versus time graph, position versus time graph. In the next one, we have a relationship represented between 2 variables. So as you can see, as the volume is increasing at this point, we can see that the vertical value, the y-axis value over here is decreasing. So as volume increases, pressure decreases. Or when the volume is got a, when the pressure's got a fairly large value, then the volume is fairly small. Okay. And another example of a graph there, we have a visual representation. Okay. And there it says, how much water do we use? Okay. And that's a pie chart. Here's some actual extracts from graphs that we also use in our everyday lives, coming from data usage on our mobile phone. They're giving us some data from, I don't know, Huawei Health or the Garmin app and so forth, right? Okay, What is expected from you in an examination in terms of working with a graph? You need to be able to analyze and explain a trend in a graph. You need to be able to read off the values, the gradient, and the intercept from a given graph. You need to be able to draw a sketch of a given situation, okay? And you need to be able to plot an accurate graph on graph paper if provided. And so we've selected a few examples there. November 2019, question 3.5, November 2020, question 3.2, November 2021, 3.3, and question 8 of November 2014. Okay. And here's examples of those graph questions. Now, what we find is that students tend to understand the physics, but they underperform in the mathematical skills, and therefore they may tend to do poorly in these questions. Okay, so those are those examples of those specific questions. Now, just in terms of types of graphs, from your mathematics class, you're very familiar with a straight line, a parabola, hyperbola. You've seen graphs representing an inverse square relationship. You've also seen a sine curve. You've seen an exponential curve. And you've also seen circles, ellipses, and cubic graphs as well, right? So these are all graphs that you are fairly familiar with. Now, important to note, when we talk about a straight line graph, you will see that certain equations are used. VF equals GT plus VI, or VI plus A delta T. That's an example of a velocity time graph. For the parabola, we have the position time graph with acceleration. So you've seen this already in your equations of motion. The pressure volume relationship you've always also seen in terms of hyperbola. Force distance with gravitation, K over R squared. You've seen this relationship as well, an inverse square relationship. And then you've also seen a sine curve. And you've definitely seen an exponential graph as well. Now, with respect to the exponentials and the circle, ellipse, and cubic graphs, those are not necessarily used as much in science experiments. But all of the others, you've definitely come across it at some point in time in your high school physics curriculum. Okay, so what we want to do is we will spend some time today to become familiar with some of these graphs, and we want to see how they relate to what we see in our physics exams. Okay, so we'll start with straight line graphs. In terms of straight line graphs, you are very familiar with the standard form of y equals mx plus c. You know what the m stands for, and you know what the c stands for. We also know that y and x represent, or the equation here represents some relationship between x and y. X is our input, y is our output. In other words, x is the independent variable and y is the dependent variable. And then we have constants. These constants are the gradients and the y-intercept. Okay, the gradient and the y-intercept. Now, why is that important? We need to know what are the things that don't change with respect to a straight line graph. Its gradient and where it cuts the y-axis. Now, another important thing to note is understanding how the slopes look. So here we see if something is increasing, in other words, as x gets greater, you can see the y value goes higher and higher. We say that something that is increasing, an increasing graph on a particular interval, has a positive slope. And this is a decreasing graph on that interval where it has a negative slope. And then over here, when there is absolutely no steepness, that's when we have a zero slope. And here, as you know, tan of 90 degrees is undefined. Therefore, we say that the slope here tends towards infinity, or it is an undefined slope for this last one over here. Okay, be very careful. Some students still think the slope here is zero, but an easy way to remember it is if I am sitting with this, there is no gradient, no slope, no steepness. That's very steep. I mean, a lot of steepness, more steep, more steep, more steep, and this is incredibly steep. So a vertical line would tend towards infinity or an undefined slope. Okay, so let's check any questions quickly. I'd like you to tell me which year has the, which graph, A, B, C, or D, has the greatest slope. Which has the greatest slope. So I see some responses coming in, and the greatest positive slope over here is B. D is a negative slope, but you can see this is quite steep. So if we look at rise over run, we 1, 2, 3, 4, 5, 6. We have 6 blocks rising over 3. So 6 over 3 that's got a gradient of 2. However, this one over here has got a steeper gradient, but it's negative, right? So that's 1, 2, 3, 4, 5, 6. 6 divided by 2, so the gradient here is negative 3. Once again, you use the rise over run. Okay. Right. In terms of equations of straight lines, we're not going to stress too much about this because you guys are all grade 12, and we trust that you are able to find the equation of a straight line. Once again, find the gradient, and then you can use the intercept to find the equation. Okay. All right. So, okay, I'm going to skip that simulation for the sake of today. But let's go to this chair hire example. So there is a guy outside Home Affairs that is renting out chairs, okay? Chair renting business. So you can go read all about, I think his name is Isaac, if I'm not mistaken. Right. I think his name is Isaac. Yeah, but anyway, let's just check quickly. Is it Isaac? Yeah. Yeah, Isaac Mpofu. He rents out chairs to people queuing outside the Department of Home Affairs in Belleville, started his business to earn a living and to pay for his university debt. He rents the chairs out 5 Rand for 2 hours, 15 Rand for the whole day, and the elderly and those with disabilities sit free of charge. Anyway, coming back to our physics. So Isaac rents out chairs, okay? What do we want to say about his chair renting business? He charges 10 Rand to hire a chair. Okay, let's not talk about whether it's whole day and so forth. And there are no other costs. So of course, if you don't rent any chairs, we are now going to look at a graph that is taking our billion rands versus a number of chairs. Okay, so if you want to construct a relationship here, we'll say, okay, it's 10 Rand to hire a chair. If I take 2 chairs, it's going to be 20 Rand. If I take 3 chairs, it's going to be 30 Rand. So in other words, it's going to be 10 Rand multiplied by the number of chairs that I want to hire. So if we look at coming up with an equation for the bill that you would have to pay, I can say that the bill measured in rands, okay, will be 10 multiplied by the number of chairs that I want to hire plus 0 rands. Now this 0 rands represents any particular fixed costs, okay? So there's an example of what my curve or my graph would look like, okay? It's going to go through 0 and 0 because if I have 0 chairs, the bill will be 0 rands and I add nothing to it, and therefore I have 0 rands. Okay, you know this distance, the change in y, or the change or the vertical change over the horizontal change, that will make up the slope, right? So that's our gradient. Okay, and we can see here that when I'm rising 10 Rand for every 1 unit that I move on the number of chairs. So the gradient here represents 10. Now, also important to note, you can see these are color-coded because M is the gradient, and that's also the coefficient of X. Here, the independent variable is the number of chairs which you wish to hire, and that is multiplied by 10. So the slope of this curve will be 10. So whatever's in front of X or whatever's in front of the independent variable in a straight line. Okay, so let's go look at a few other examples. If he charges 8 Rand per chair and no other charges, what will this initial blue line is what we were looking at first in terms of the 10 Rand. But if he charges 8 Rand per chair and no other charges, then this is going to be the curve or the graph that I'm looking at. Okay, and why are we saying that? Well, firstly, I think that we can't particularly see it on screen there. I see the banner is on there. So what I'm going to do is I'm going to just write here. So here you can clearly see that B is equal to 8N and no other charges, right? Which means that M here is equal to 8, right? Because that's my gradient. This is my M. This part over here is my C. And so therefore we say that C is equal to 0. Okay. Right. Let me just quickly. Okay. Thank you, Amir. Much appreciated. Okay. So for the next one, the chair is charged at 8 Rand per chair, and there's a 20 Rand admin fee. Now, the 20 Rand admin fee is irrespective of whether you're going to hire a chair. Oh, no. You're going to hire a chair, but you're going to pay a 20 Rand admin fee, whether you pay for one chair, whether you pay for 10 chairs or 20 chairs, right? Which means that if you think of this, this is like your itemized billing fee on your cell phone contract. Whether you make any calls or not, they're still going to charge you itemized billing if you take out a cell phone contract, right? So irrespective, you must have an amount of 20 Rand at least that you will pay. So in other words, we will start here with 20 Rand on the y-intercept, okay? And if you hire one chair, then you're going to pay 20 Rand plus 8 Rand, which would then be 28 Rands, which means that this intercept over here is going to be 20. Okay, so here we can see it's still 8 Rand per chair, so it's 8 Rand times the number of chairs plus 20. 20 is a fixed cost, and that fixed cost represents the y-intercept. Okay, now the last one is the chair is charged at 15 Rand per chair, and the first chair is free. So in other words, you're going to get one chair for free. So let's think about this. If I hire 10 chairs, then I'm only going to pay for 9. If I hire 5 chairs, I'm only going to pay for 4. Okay? And there we go. That equation is going to look like this. 15 Rand multiplied by how many chairs I'm going to pay for, which is n minus 1. And because there was no other charges, it's going to be plus 0. However, since the first chair is free, whatever is corresponding to 1, we will have an intercept of minus 15. Okay? And remember, when you multiply this out again, this is going to give you 15n minus 15. So the y-intercept of this graph will be negative 15. Okay, so why all this babble about graphs? Well, we want to see where these apply to in physics. So if you go back to the previous slide, there you can see that's all physics, all basic chair examples. And then here we can see, okay, there's an example of Ohm's law, right? I is equal to V over R. But if I is equal to V over R and the relationship is demonstrating I versus V, then what we will have is I over R as the gradient. So you can clearly see that in this graph, the gradient is 1 over R, okay? And the y-intercept is 0. In this graph over here, we have an example of velocity versus time. Well, you know, in velocity versus time, the gradient over there is acceleration. And there we can see it's A delta t plus VI. So VI, you've seen this in equations of motion, maybe turned around a little bit. We have VI plus A delta t. But the coefficient of delta t, because t is the independent variable, gives you the gradient. The gradient of a velocity time graph is therefore acceleration. Okay? And then in the last question over here, if you've not covered the photoelectric effect just yet, you can clearly see that E equals H, F minus F naught, right? Now, what is F naught? HF naught is the work function, right? So if you've given energy in joules versus the frequency, the y-intercept over here will represent what's known as the work function. So students must make the relationships between the graphs that they already know and being able to apply them in physics contexts. My apologies. Another important thing to note, let's use a simple example. You may encounter a question in electricity, and that question will involve maybe a graph of voltage versus current, for example, right? And if a student knows or figures out that they know that the gradient, which is the change in y over change in x, represents, for example, the resistance, then it's important for the student to actually make it the change in the voltage divided by the change in the current, because they must identify to use a physics-specific formula to answer that question, okay? So be precise about that as well, and we'll obviously look at some examples as time goes by. Okay, here's an example taken from Dr. Fish, where he's using a real-life example of airtime remaining versus minutes used, okay? So if calls are charged at 2 Rand per minute and initial airtime was 200 Rand. In other words, this person has a cell phone contract. He's given 200 Rand, but the 200 Rand decreases as they talk on the cellular phone at 2 Rand per minute. Okay. So if you wanted to know how much airtime do you actually have, it's going to be 200 Rand minus 2 times the time that is spent on the telephone in minutes. Okay. So again, look at the example given on top. Y equals mx plus c. Again, m is the gradient. Okay, sorry, m is the gradient, c is the y-intercept. So this will be your y-intercept. You can see there it cuts at 200. Then the gradient, of course, it slopes downward if it's negative, and therefore you can check your intuition. Something that slopes downward to the right will be a negative gradient, and here you can see the gradient is minus 2. And then the independent variable will, of course, be the time in minutes. So if you speak for 10 minutes, it's going to be 2 Rand times 10, which is 20 Rand. And that's how much money is going to be taken from your airtime. And therefore, we get minus 2 times 10. Okay. Now, here we go. Here's an example of the exact same thing. But here's a physics example. There was a real life one, now a physics one. Here's an example of voltage versus current. Okay. And you know what the definition of the EMF is. It's the maximum potential difference that a cell can provide to the external circuit when it's not in operation. So if you go to the shop and you read that I'm buying a 1.5 volt battery, what's quoted on that battery will, of course, be the EMF, the maximum potential difference, right? Okay, so now, here you can clearly see, once again, straight line, y equals mx plus c. M is the coefficient of x, so therefore m is the gradient. C is the y-intercept. In other words, it's the constant that we see over there. That y-intercept in V equals I times little r, right, plus EMF will be the EMF on this side, okay? The resistance obviously causes a decrease in the voltage, and therefore we have the minus R over here, and over there we have the current. Okay. So there's E internal resistance there, and there's current over there. So once again, being able to read this off the graph is critically important for you. Okay, let's look briefly at quadratic graphs and parabolas. When you're graphing quadratics, let's talk about a few things that you're familiar with. I'm not going to go into the simulation over here, once again, for the sake of time, but a few things that you know. Depending on the coefficient of x squared, that will tell us how steep a particular graph is. Okay, so the graph of 2x squared will be a lot steeper than the graph of a half x squared, for example. When we look at a parabola, and I haven't included a plus c there, ax squared plus bx plus c, if we talk about whether the constants, whether the numbers that don't change over here, it's going to be the coefficients of x squared and the coefficient of x. And of course, the independent variable is once again our x, and our dependent variable is our output, which is y. Okay. So here's a physics example of something we have seen. We've seen position time graphs. Okay, and we've seen that the coefficient of delta t squared or time squared is a half a, and we've seen that the coefficient of delta t is the initial velocity. So there it gives us something relatable. Okay. Now, before we come back to parabolas, let's revise some of your important work from grade 10. One of the important things that students must remember is to read the axes on the graphs. Identify what you are actually measuring or representing in terms of that relationship. Sometimes students get a position time graph and they're talking about, I don't know, acceleration or velocity, or they're reading off a particular y value that doesn't actually describe the thing that they are speaking about. So in terms of position time, in grade 10, you covered this thoroughly, okay? Position versus time simply tells us where somebody is with respect to a particular reference point over time, okay? So what can we say is happening with this red line or this red curve that we find over here? Well, as time is increasing, the position away from a particular reference point is increasing. Okay. What can we say about the green line? Well, it's also increasing, but it's increasing at a faster rate because it has a much steeper slope. Okay. So if we think of this as somebody moving away, I'm standing here and then I'm moving to that side and I'm walking away at a constant rate, my position will then increase as time goes by. Okay. The green graph, on the other hand, is also moving away, but moving away much faster. Okay. Righto. So for the next one, if we look at this piece over here, if I read the y value, the corresponding y value over here, we see that the y value is not changing as the x value gets bigger and bigger. In other words, as time continues, the position is not changing. So in a position time graph, we interpret this to be somebody is standing still, right? They're not moving, okay? They were moving away from that particular position. The green one is they were moving away much faster. The blue line over here is actually saying somebody's standing still, okay? Now, what's happening over here? Here, the position away from the particular reference point is decreasing, which means you're returning to your origin. So if we highlight, before we come to that blue curve, if we highlight, okay, let's talk about the blue and purple curves one time. Of course, with the blue and purple curves, you can also see its position time graphs. So the rate at which they are moving is changing, right? Here, the rate is not changing. Here, the rate is changing. So when the rate is not changing, we say that there is zero acceleration, right? Here, they're standing still, so zero acceleration and standing still. Here, also zero acceleration because these are moving at constant velocities. On the other one, on the other hand, if we just look at this blue curve over here, I don't know, is the banner still there for our one comment? Thank you, Samir Jones. We just got two highlights here below. If we look at this blue curve, the rate first is slow, then is moving faster away, right? So there is definitely acceleration there. Then on the purple one, it's first going to be quite fast, then they're going to move slowly away. Okay. Okay. Right. Now, I just want to see these two dots. Oh, we can see those yellow dots. Those yellow dots, that's lying. What does it mean? Now, on a position time graph, the yellow dots being on the same horizontal axis indicates that they represent a person standing on the same position because the position is equal there. Okay. Let's change this a little bit and go to a velocity versus time graph. Now, velocity versus time, here we had position versus time. The two yellow points we can see is exactly the same point. They're standing at the same point. So in the last few minutes, let us look at a velocity time graph. Okay, and what's happening in this velocity time graph? In the red curves that we see over there, right? Here we can see that between this time and this time, the velocity is increasing. In other words, the velocity is getting larger with respect to time. Here, the velocity is also increasing. However, if I compare the first or the left-hand side red line or red curve or part of the curve with this part over here, we can see that this is increasing. This is increasing at a faster rate. Okay, so there's constant acceleration. Here's constant acceleration, but this is at a steeper gradient, so faster acceleration, right? Then the velocity remains constant on the blue line. And if the velocity remains constant here, it means that over time, we're traveling at a constant velocity, and constant velocity means zero acceleration. And then for the last part over here, the velocity decreases. Okay? the velocity decreases. Okay. Now, if we go back to our yellow points over there, if you just read the graph, this corresponds to a y value of 0. So whereas in the position time graph, we were standing on the same spot, okay? In the velocity time graph, on the other hand, this indicates not necessarily the same spot, but most definitely that the person has come to a standstill, that they are no longer moving. Okay. We have about 4.5 minutes left quickly. Let us quickly talk about this. And in our next session, which is sometime this week, we will go into more detail with the rest of these graphs. So let's compare quickly position, velocity, and acceleration. When there is a constant velocity, your velocity time graph will have no acceleration. In other words, your acceleration graph will be on the x-axis and just one horizontal line. For the velocity time graph, since it's constant, some constant positive velocity, it will be above the x-axis at a straight line. And because you're moving at a constant velocity, your position time will increase at the same rate as you go. Okay. If there's positive acceleration, because you're moving faster, that means that your velocity will increase over time. It also means that your position versus time graph will be a parabola, right? Because you're moving faster, so eventually you're accelerating, and therefore you're going to cover more and more distance per time unit, and therefore you see a little bit of a power curve there. Okay. If there's negative acceleration, then of course the acceleration itself is negative. The velocity will tend to decrease, and also until you reach a point where you change direction, and your position time will look like this, right? You will plateau and then you will change direction as well. Okay. So we will call it a day for today. In the next session, which will likely be sometime this week, we will look at a few simulations to depict these graphs, and then we will move into dealing with these graphs in terms of physics examination questions for the NSC examination. Okay, so for today, thank you all for joining us until our next session, in which we will tackle graphs in more detail and also see a few examples from the NSC examinations. Thank you from me, and over to you, Amir, in studio.
We say shukran, jazakallah khair, and baik terima kasih. Thank you very much to Brother Imad Isaacs for so beautifully giving over session 1 of the physical sciences preparation to all of you, our matriculants out there. I will say, based on the time that I have here, that this was definitely the longest session that we have had of all the sessions. So I hope that everyone have benefited, alhamdulillah. And as a reminder, once again, respected viewers, please, if you have family and friends who are in matric, who are preparing for their trial examination, please forward this to them, especially if they're physics students. Please forward this to them, inshallah. Share this with them in order that they may benefit and also prepare adequately for their physical sciences paper, inshallah. Once again, not only to our beloved brother Imad Isaacs, our instructor for the session, but to all of you, our beloved viewers, we thank you very much for joining in. Until our next session, inshallah, we wish you very well. Wassalamu alaikum wa rahmatullah.